Adaptive mesh refinement increases accuracy by refining the mesh where it is needed, while keeping the mesh coarse in other areas. Hello, I'm Armin. In this video, I'll explain how to use adaptive mesh refinement with two different methods. Before we start, I'll briefly explain what adaptive mesh refinement is. The adapt mesh operation modifies an existing mesh based on a specified expression. Most commonly, it refines the mesh using error information from a previously computed solution, making it a key component of adaptive mesh refinement. It can also be used without a solution by adjusting the element size according to a user-defined size expression. This allows you to control the mesh distribution based on your own criteria, rather than solution errors. COMSOL provides three types of expressions: absolute size, anisotropic metric, and error indicator. In this tutorial, I'll focus only on the error indicator, which is the option I'll use for adaptive mesh refinement. The error expression list allows us to define the quantities used for mesh refinement. For example, we can use dependent variables such as velocity or pressure. We can also use other expressions, including field variables and their derivatives, as long as they are defined in the domain. COMSOL provides three adaptation methods for refining the mesh. The first method is general modification, which is the default option. It modifies the existing mesh by combining refinement, coarsening, topology changes, and mesh smoothing. This method offers the greatest flexibility. However, if your model contains boundary layer or other anisotropic elements, it is recommended to disable Allow Coarsening. Otherwise, the boundary layer structure may be degraded. The second method is Regular Refinement. Instead of changing the mesh topology, it uniformly refines selected elements by bisecting all of their edges. This preserves the overall mesh pattern and produces a more predictable refinement. The third method is Longest Edge Refinement. In this approach, only the longest edge of each selected element is bisected, and the process continues recursively where needed. This typically introduces fewer new elements than regular refinement, but it is less suitable for meshes containing non-simplex elements. For this example, I'll use the backstep model from the COMSOL Application Library. For the mesh adaptation, I'll select Regular Refinement as the adaptation method. As the error indicator, I'll use the velocity magnitude, represented by SPF.U. This means that the mesh refinement will be driven by the velocity field, with greater refinement in regions where the velocity changes or reaches higher values. After applying the mesh refinement, we can see that the velocity contour changes slightly compared with the original mesh. That explanation is enough. Let's get started. To start, let's use a model from the application libraries. Click File and select Application Libraries. In the search bar, type backstep and click Search. Under Single Phase Flow, select Backstep and click Open. This is a flow model. First, expand the component node. As you can see, it uses the laminar flow interface. I want to change it to a turbulent flow model. In the Settings window, set the turbulence model type to RANS and then change the turbulence model to K omega. This model is more suitable for internal flows. Before we begin, let's take a look at the model. Go to Geometry 1, click Union 1, and select Build Selected to display the complete geometry. As you can see, the geometry is split and only a section of it is used. This approach helps reduce the computational cost. Now I'll collapse the geometry node and expand turbulent flow, K omega. Here we can see the inlet boundary condition applied to the tube, the symmetry boundary condition applied to the cut surface, and the outlet boundary condition applied at the exit of the geometry. Now let's generate the mesh. Click Mesh 1. For this example, I'll use a coarser mesh to reduce the computational cost, and then click Build All. The mesh is now generated. I've intentionally used a coarse mesh because we'll refine it later using Adaptive Mesh Refinement. Before we can do that, we first need to solve the model. Go to Study 1, click Compute, and wait for the solution. The computation takes about 2 minutes. Once it's finished, we can examine the velocity, pressure, and velocity streamlines. As you can see, this mesh is too coarse to accurately capture the flow features. To improve the solution, we'll use Adaptive Mesh Refinement, which you can find under the Mesh tab. If I expand Modify, you can see Adapt. However, we cannot use it with the current mesh sequence. We first need to create a new mesh sequence. The easiest approach is to right-click Mesh 1 and select Duplicate. I want to keep the original mesh and perform the adaptive refinement on a separate mesh sequence. Now expand Modify and select Adapt. In the Settings window, notice that the adaptation requires an existing solution. By default, it uses Solution 1. You can find Solution 1 under Study 1 by expanding Solver configurations. So Adapt 1 uses the solution from Study 1 to estimate where the mesh should be refined. All the mesh sequence operations have been removed, so no mesh will be generated. If I click Build All, nothing happens. Why is that? Because I didn't enable the physics-induced sequence option, the mesh operations were deleted. To fix this, I'll right-click Mesh 2 and delete it. I need to switch to a manual mesh. To do that, right-click Mesh 1 and select Edit Physics-Induced Sequence. This converts the automatically generated mesh into a manual mesh sequence, making all the mesh operations visible. Next, right-click Mesh from Physics and select Duplicate. Then go to the Mesh tab, expand Modify, and add Adapt again. Now, if I click Build All, COMSOL starts generating the adaptive mesh. However, we encounter a warning because Allow Coarsening is enabled. Since the current mesh is already coarse, COMSOL attempts to coarsen it further, which can lead to mesh distortion. I'll explain how to disable it further. Now, let's take a look at the available settings. Under Type of Expression, there are 3 available options. By default, Error Indicator is selected. In the Error Expression field, we can specify any solution variable to control the mesh refinement, such as velocity, pressure, shear rate, or other derived quantities. For this example, let's use velocity. Go to the velocity plot, expand Surface, and copy the expression spf.u. Then paste it into the Error Expression field of Adapt 1. Before rebuilding the mesh, let's take a look at the velocity contour. The red and green regions have much higher velocity than the blue regions. Therefore, these high gradient regions should receive additional mesh refinement. Now, paste the velocity expression into the Error Expression field and click Build All. As expected, we encounter another warning. Let's see why. Go back to Adapt 1 and scroll down to Adaptation method. It is better to disable Allow Coarsening because we don't want COMSOL to coarsen the original mesh. This is one of the main reasons why mesh distortion can occur. Now click Build All again. This time, the mesh is generated successfully. Let's compare Mesh 1 and Mesh 2. As you can see, the mesh has become much finer in the regions with higher velocity. Now, let's try a different refinement criterion. Instead of velocity, let's use shear rate. The corresponding expression is SPF.SR. To find these expressions, open any result plot, click Surface, and then select Add Expression. From there, you can browse and choose any expression you want to use. For example, I'll search for shear rate using the filter box and select the corresponding expression. I'll return to Adapt 1 and click Build All again. As you can see, the refinement pattern changes because it now follows the shear rate distribution. Next, let's see what happens if we use pressure instead. Enter P as the pressure expression and click Build All once more. Again, the mesh changes according to the pressure distribution. For now, we'll ignore these mesh warnings and switch back to the velocity expression. Now let's look at the available adaptation methods. If I open the drop-down menu, you'll see three options: General Modification, Regular Refinement, and Longest Edge Refinement. The first option, General Modification, modifies the overall mesh morphology. While it provides more flexibility, it can produce low-quality elements when the initial mesh is already coarse, as in this example. The second option is Regular Refinement. Instead of changing the mesh topology, it simply bisects the selected coarse elements, preserving the overall mesh morphology. Let's build the mesh and see the result. Compared to Mesh 1, you can see that additional nodes are inserted into the existing elements, while preserving the original mesh structure. This is generally the preferred method for adaptive refinement. Now, let's select Longest Edge. This method identifies the longest edge of each selected element and bisects it. Like regular refinement, it largely preserves the original mesh morphology. Now click Build All. As you can see, only the longest edges of the selected elements are divided. If we compare this mesh with Mesh 1, the refinement pattern becomes much clearer. In most cases, I recommend regular refinement because it preserves the mesh structure while providing a reliable refinement strategy. The maximum number of refinements specifies the maximum number of refinement passes that COMSOL can perform. By default, this value is set to 5. Next is the element count growth factor, which controls how much the mesh is allowed to grow during each adaptation step. For example, a value of 1.7 allows the number of elements to increase by approximately 70%. You'll also find options such as fraction of worst error and fraction of elements. These parameters control how COMSOL selects the elements to refine. If you'd like to learn more about them, you can refer to the COMSOL documentation. Now click Build All once again. Before solving the model with the new mesh, let's compare Mesh 2 with Mesh 1. As you can see, the adaptive mesh is much finer in the high velocity regions, while the areas with very low velocity remain almost unchanged. Keep in mind that the adapted mesh is generated by refining the existing mesh rather than creating a completely new mesh from scratch. Now let's solve the model using this refined mesh. Since the mesh has changed, we need to create a new study. Go to the Study tab, click Add Study, and just like Study 1, select Stationary. Everything looks good so far, but before computing the solution, it's a good idea to verify the mesh selection. Expand Mesh Selection under the Stationary Study step, and notice that Mesh 2 is selected automatically. If we switch back to Study 1, we can see that it still uses Mesh 1. Now, return to Study 2 and uncheck Generate Default Plots, since we don't need another set of default results. Click Compute and wait for the solution. Once the computation is complete, let's compare the results with those from Study 1. To do that, duplicate the velocity plot and rename it Velocity/Adaptive Mesh. Next, change the dataset to Study 2 and display the new result. As you can see, the velocity contour has changed. If we compare it with the result from Study 1, both the maximum velocity and the contour distribution are slightly different. Finally, go back to Adapt 1. You can experiment with different adaptation methods, different element growth factors, and different error expressions. For example, if you use shear rate, the mesh becomes finer in regions where the shear rate is highest. As you can see, using velocity as the refinement criterion produces a much finer mesh in the high-velocity regions. Notice that regular refinement is usually the safest option because it preserves the original mesh topology and minimizes the risk of mesh distortion. Alternatively, you can refine the mesh based on pressure instead. Enter P as the pressure expression and click Build All. This time, the mesh is refined mainly near the walls and at the inlet, where the pressure gradient is higher. If we compare this mesh with Mesh 1, we can see that the expansion region changes very little because the pressure gradient there is relatively small. This completes the first method of adaptive mesh refinement in COMSOL. Now let's move on to the second method. The second method is much simpler than the first one. With this approach, there's no need to create a new mesh or a new study. Instead, we can enable adaptive mesh refinement directly in the Study 1 settings. Go to Study 1, select Stationary, and then under Adaptive Error Estimate in the Settings window, enable Adaptation and Error Estimation. Under Adaptation Method, you can choose any of the refinement methods we discussed earlier. For this example, I'll select Regular Refinement. Under Error Estimate, there are 3 available options: L2 norm of error squared, function, and error indicator. For this example, I'll select Error Indicator, just as I did in the first method, so the mesh refinement is performed using the same criterion. If you'd like to learn more about the other error estimation methods, you can refer to the COMSOL documentation. Now click the plus icon to add an error expression. As before, we'll use the velocity magnitude. You can find this expression in the velocity result. Expand Velocity, select Surface 1, and copy the expression shown in the Expression field of the Settings window. Then return to Step 1 and paste it into the Error Expression field. Everything looks good, so now all I need to do is click Compute and wait for the solution. One limitation of this method is that you can't preview the adapted mesh before solving the model. As a result, you also can't identify any potential mesh warnings until the computation is complete. The solution is now complete. I forgot to uncheck Generate Default Plots in Study 1, so I'll delete the automatically created wall resolution, pressure, and velocity plots. Before examining the results, let's take a look at the generated mesh. Go to Component 1 and expand the Meshes node. As you can see, there are now 2 separate mesh sequences. Mesh 1 is the original mesh, while Level 1 Adapted Mesh is the refined mesh. As you can see, the adapted mesh is identical to the one generated using the first method because we use the same error indicator based on the velocity magnitude. Now let's compare the results. I'll duplicate the velocity plot. Right-click Velocity, select Duplicate, and then change the dataset to Adaptive Mesh Refinement. Click Plot to display the result. Notice that there are 2 available parameter levels. Level 0 represents the original mesh, and level 1 represents the adaptively refined mesh.
Take a look at the contour color bar to see the difference between the two solutions. Another limitation of this method is that the solution on the original mesh must be computed again before the adaptive refinement is performed. As a result, it generally takes longer than the first method. To change the refinement criterion, simply go back to the stationary settings and modify the error expression.
You can also experiment with the functional and L2 norm of error squared error estimation methods. For more information about these options, refer to the COMSOL documentation. In addition, you can change the adaptation method to general modification, longest edge refinement, or rebuild mesh. The rebuild mesh option is available only in the second method. This was a general introduction to adaptive mesh refinement in COMSOL. If you found this tutorial helpful, please like the video and subscribe to the channel. Thanks for watching.